Now we need a way to name these enantiomers of each other, and so we're going to have to designate the position of each of these groups. And we do that using this system. We're going to assign priorities to each of the four groups, rotate it so the number 4 is on a dash, look at the sequence 1, 2, 3. If it's counterclockwise, it'll be an S configuration. If it's clockwise, it'll be an R configuration. So we're going to go over each one of these with some practice problems. So the first thing I said was that we're going to assign priorities to the groups. The atoms with the highest atomic number are given the highest priority. So for this is a chiral carbon right here. We've got a hydrogen, a carbon, an oxygen, and a chlorine. Well, chlorine is number 17 on the periodic table, and so it has the first priority. Oxygen is a number 8, and so it's got the second priority. Carbon is third at 6, and hydrogen, of course, just has atomic number of 1, so it's number 4, the least priority. Okay, so of course, it's not always that easy. Look at this chiral carbon here. It's got a hydrogen and it's got an oxygen. So the hydrogen is going to be number 4. Pretty sure about that. The oxygen is going to be both these carbons, and so it will be number 1. But how do we decide which carbon comes first? Well, we look at what else it's attached to. Well, each of these has 2 hydrogens and 1 carbon. So these are identical. We have to move out to the next carbon. This carbon is attached to 2 carbons and a hydrogen. This carbon is attached to 1 carbon out here and 2 hydrogens. And so this side wins, and it gets to be number 2, and this side is number 3. So let's look at another example. Very similar. We've got a hydrogen. We know that's going to be number 4 because with an atomic number of 1, nothing's going to compete with that. And we've got 2 carbons, and this is an oxygen, so the oxygen is going to be number 1. We need to decide which one of these is going to win. So this carbon, these are both carbons. This carbon is attached to 3 more carbons, here, here, and here. This carbon is attached to an oxygen and 2 hydrogens. Oxygen has a higher atomic number, and so this will be number 2 and this will be number 3. So let's look at this one. This is our chiral carbon, and it's attached to carbon all the way around. So we're going to be comparing these carbons. This carbon is attached to a hydrogen, and a hydrogen. That's going to probably make it number 4, but let's go around and check. This carbon is attached to another carbon and 2 hydrogens. And this carbon is attached to a carbon and 2 hydrogens. Uh-oh, they're tied again. So we have to go out again. This one is attached to 3 hydrogens, and this one's attached to a carbon and 2 hydrogens. So this one, the long one, will be higher priority than the short one. And that's a rule in general you can just count on. If it's a longer one, it'll be, if it's a hydrocarbon, the longer hydrocarbon chain is going to be more important. Okay, so let's look at this one. This one is attached to a carbon. It's attached to 2 oxygens. So it's going to be number 1 because of the oxygen that's attached to it. And because it's double bond, we count that oxygen twice. That occasionally comes into play. Okay, so we said this was number 1. This one will be number 2 because it's longer. This one's number 3, and this one's number 4 because it's the shortest. Methyl groups will frequently be number 4 if there's a hydrogen not present. Well, in fact, if hydrogen is not present, the methyl group will be number 4. Okay. So we know how to assign groups. The next thing I had written down was that we were supposed to rotate the molecule. So I'm going to show you something with my models here. I've got them set up so that they're identical. Okay, the green's on top, the yellows are beside each other, the reds are beside each other, the blues are beside each other. If I switch any 2 groups, and it doesn't matter which groups I switch, I will make the mirror image. I've got the mirror image made. If I again switch 2, so these are enantiomers, and it doesn't matter which 2 I switch, just pick 2 and switch them, I am back to identical molecules. These are the same. So we can use this rule to rearrange our partners to get that number 4 on the wedge, not the wedge, the dashed that we need it to be on. Okay, so we're going to rotate the molecule. We find the 4th priority and switch it with the group that's on the dash. Find number 4 and switch it. With the dash, and then we need to switch another group. It doesn't matter which group we switch as long as we keep the number 4 on the back. So in this example, 3 is on the back and 4 is on a line. So we switch 3 and 4. This is the enantiomer. If we switch another 2, and it doesn't matter which ones, we'll be back to the same molecule. So designating the configuration here. So here we've got a hydrogen, that's going to be number 4, and a bromine, that's going to be a number 1. Then we've got a methyl group on this side, and over here we've got a longer chain. So the methyl group is going to have a lower number than the longer chain. Okay? Now we need to do some switching because our hydrogen, our number 4 group, is on a wedge and not on a dash. So I'm going to get a different color and do some switching. I'm not going to switch the compounds here. I'm just going to switch the numbers. And when I switch them, it does not mean that bromine is number 4. It just means I'm switching the numbers. So we're going to put 4 here. 1 will be here. Then we also need to make another switch because this is the enantiomer. So we'll need to switch another number. We're going to switch the 1 and the 2. So the 1 will be down here and the 2 will be here. Now we're going to ignore the 4 and we're going to see whether the 1, 2, 3 go in a clockwise or a counterclockwise direction. So 1, 2, 3. Well, we're going, that's the way the clock runs, and so this is an R configuration. Let's look at this one. It's important first to find the chiral carbon. There is a hydrogen that we don't draw usually, and it's going to be on a dash. So that part's already done for us. We know the chlorine is going to be number 1, and the hydrogen is going to be number 4. Let's look at our carbons and see if we can figure out them. Here we've got a carbon, and here we have a carbon. So which carbon is the more important one? It's going to be this one. It is officially bound to 3 carbons. Count the 1 carbon here, and because that's a double bond, we count that one twice. This one is bound to 2 carbons and a methyl group. So this will be 2 and this will be 3. We already have our 4th group on a dash, and I'm going to get a different color. We go 1, 2, 3, and we've got another R molecule. So let's look at this one. First, we find our chiral carbon. It's right here. And it looks to me like we've got carbons everywhere, all the way around. So first, let's look. This one is the methyl group, and it's going to be the shortest. So we'll make it number 4. The ethyl group, I'm going to make number 3. And then we need to choose between these. Got a carbon here, and it's attached to a carbon and 2 hydrogens. This carbon here is attached to 2 carbons and 1 hydrogen. So it will be number 1, and this will be number 2. Looks like we're going to have to do some switching here because we've got the 4 coming toward us, and we're going to switch the 4 and the 3, and then why don't we switch the 1 and the 2. Okay, so if we connect the things, go 1 to 2 to 3, we're going counterclockwise. That's the S position. Okay, so now I want to show you a trick so you don't have to do so many rearrangements. So here we have a molecule. We're going to say that the green here is the 4th group. So we want it back, and we're going to say that we're going red, yellow, blue. So I see a clockwise direction, red, yellow, blue. If I look at this molecule from the other side, so that now the 4th group is facing me, red, yellow, blue appears as being counterclockwise. Red, yellow, blue is now counterclockwise. So if you're looking at a molecule and the 4th group is facing you instead of being away, like it's supposed to be, you can just reverse the direction. So when I see this molecule, I see red, yellow, blue, counterclockwise, but I know that red, yellow, blue is actually clockwise, and so this would be an R configuration if red, yellow, blue was the correct order.